Hi there, it's Manuel for Intagma, today with a tutorial about connecting yarns using the PBD solver, that is, the grain solver in Houdini. It's a straightforward setup, so let's directly dive in and get started. First, let's create some yarns, so put down the grid and dive in, and we will make it a little bit smaller, like 1, 1, and now append transform. Rotate it by 90 degrees, like so, and move it in the Z direction, like so. This is the first plane that we want to use to scatter points onto to originate our yarns from. Now let's duplicate this transform and just shift it over to -1. Now we have a second plane. This is the end point of our yarns. Now we need points, so put down a scatter. Not too many, because we don't want 1000 yarns, so let's scatter 50 points here, and append the same scatter to the other side. But be careful, because we don't want to have exactly the same distribution, and this is what it does by default. So let's change the seed to something different here on this second one, and now you have 50 randomly distributed points on both planes. And now let's create some yarns between these points. I like to do this with a wrangle, so put down a point wrangle, connect the left points into the first input and the right points into the second input, and rename this to add lines or add yarns, like so. Now Alt-E will give the expression editor. Let me make this a little bit smaller for you to see the entire window. And now it's very straightforward to connect yarns. Remember that this wrangle will execute on the first geometry stream, so on the first 50 points. The second 50 points are not present. So we will add these points to the geometry stream. So create an integer new point, and let's add with add point. Let's add points at the location of the point from the second geometry stream. And that can be done with the shortcut syntax of op input 1, which is the second geometry stream, and then p. That means as the points have the same IDs in the left stream and in the right stream, we can use this syntax to directly access the position of the points in the second stream. Now that we created new points, let's quickly check if this works. And you see, it does not work, because I made a small typo. It's not opt, but op input. And now it's able to access the position and create the new point. Now we have 100 points. If I middle click here, we have 100 points in our geometry stream. Time to add the primitives. So again, Alt-E for the editor and add primitive. New prim is add prim. Geometry stream is 0, and the prim has the type polyline, because we want to create open polylines. And now it's time to add vertices, so add vertex. The first vertex is in geometry stream 0, the primitive is nprim, and the first point is ptnum, the currently processed point, and then the same statement again, but for the second point. And the second point is our new point. Now that we have that, we have primitives between these points. Great. The next step is to prepare the geometry for the PBD solver. And the PBD solver needs some attributes on the geometry to be able to do its work. At the moment, we have single primitives. You can see this if I turn on primitive numbers. Every line is one primitive, and we have just 2 points on these lines. That's not good for simulation, because the PBD solver simulates points, so we need more points. So let's put down a resample and add more points to this, maybe decrease the length a little bit to add really a lot of points, because the more points you have, the more exact the simulation will be. Now we have a lot of points. The PVD solver solves the points, and it treats primitives between the points as constraints. But at the moment, we only have one primitive with a lot of points. What we want to have is single primitives connecting only 2 points at a time. And fortunately, there is this nice convert line HDA that is part of Houdini that does exactly this. It creates individual primitives connecting 2 points. So instead of having one large line, I have now many individual lines connecting 2 points. That is exactly what we need for the solver. And as a nice side effect, it gives me a primitive attribute called rest length, because this rest length is very important too. It's just the length of the primitives in rest state, so in this not simulated state. And this attribute, this primitive attribute, is needed by the PVD solver too. We get this for free with the convert line. Before we continue, let's do one thing that is necessary later on, because later on I want to connect between these original primitives here. And for this to work, I need the information to which original primitive the points belonged when I created them. And as soon as I do this resampling convert line, I don't have the original primitives anymore. So this information has to be stored on the points after the resample, but before the convert line. So let's create another point wrangle. Here it is. And we want to use this to set a new attribute. The attribute should be called myPrim, and it stores the information to which primitive the point belongs. So the attribute is an integer, myPrim, because the primitive IDs are integers, and it has to store something. But how can we access the information to which primitive the point belongs? Well, there is a nice vex function called pointprims, and it gives me exactly this information. But because the point can belong to many primitives, it returns an array. So let's first create an array, integer myprims, and then square brackets to indicate that this is an array, and then pointprims, and pointprims geometry stream 0 of our current point, which is pt num. So now this returns an array of all the primitives that pt num, the currently processed point, belongs to. In our case, it's only one primitive, the very first one. And the very first one has the array index 0. So what we can do is we can write myprims, which is the array, and then just 0 and store this to the new attribute. If we do that, we get a new point attribute called myPrim, and you see that it just counts from 0 to 49. That means 50 primitives. Every point now stores the information to which original primitive it belongs. Here. So rename this to add myPrim. And now I can do the convert line and have still maintained the information to which primitive the points originally belonged. Let's continue with setting up the attributes that are needed by the PVD solver. Another wrangle. Here to add some tension. We want to halve the rest length, because then the solver will try to achieve a smaller rest length than the current length, and this will give tension to the constraints. The constraints are primitives, so this has to be a primitive wrangle, and then just type rest length times equals 0.5. This is shortcut for rest length is rest length times 0.5. So after this statement, we have half the rest length than before. Half rest length. Let's check. Here we have a rest length of 0.009 and so on. And here we have 49, so half of that. Great. The next thing that is missing is the mass, because we want to set a mass for the solver to use, and we want to set a different mass at the endpoints and at all the other points. because we want to pin the endpoints in space. And that can be achieved by just putting the mass of 0 on them. But we have to somehow differentiate between the endpoints and all the other points. And so let's create a group through an expression. Use the new group expression node. And with this, let's put in a statement to create a group. The group will be called ends, which criterion can be used to distinguish between all the intermediate points and the endpoints. Well, the endpoints only have one neighbor. So we can use that to create a group. So let's state neighbor count of geometry stream 0 ptnum should be smaller than 2. And this gives all the endpoints in a group, as you can see here, because these endpoints have a neighbor count of 1 and not 2. Now that I have that, we can append another wrangle, point wrangle, and we use this point wrangle to set the mass for all the points. And that means we just type in at mass is 1. And at the same time, we can set p-scale. That is a value that is needed by the solver too, because it determines the radius of the individual particles regarding collisions. So now all the points have a mass of 1 and a p-scale value of 0.001. So set mass p-scale all. And after that, we can append another wrangle, but this time let's make it run only over the ends group and override the mass with 0. Call this set mass ends. And after this wrangle, the endpoints will have a mass of 0 and all the other points will have a mass of 1. Let's quickly check this. And if you see here, we have a mass of 0 on this point and a mass of 1 on this point. P-scale is unaltered, so it's 0.001 on all the points. Now we have everything set up for the PBD simulation. Let's continue by creating a popnet. So popnet, make sure to use a new one, and let's feed the geometry into the first input of the popnet, and let's dive inside. Inside we get particles on the primitives. That is not what we want. We have to change the source here. The source is in charge of creating the particles, and at the moment it's set to scatter on surfaces. What we want to use is all geometry. All geometry means it not only uses the incoming points, but it uses the primitives too. And as the primitives are used by the grain solver to set the constraints, it's necessary to keep them here. But this node is executing on every frame. Here on the birth tab you have an impulse activation set to 1, and we only want to add the geometry once. So let's quickly put an HScript expression here to make sure that it only executes once. $f, which is a current frame, should be 1 for this to be true. So on frame 1 it's true, so the geometry gets added only once. If we now press play, nothing happens. Let's turn off the guide geometry. Here you have the geometry. But if we now add a gravity force here down there, because we want to affect everything in the geometry stream here, everything falls down. And you see that the points that have a mass of 0 stay where they are, because without a mass they don't simulate. But of course, the stuff is just falling down. We need some solver to make the yarns behave as yarns. And this will be accomplished by the pop grains. The pop grains is PBD. We add it here. If we now press play, it still just falls down. Why is that? Because it's not taking the constraints into account by default. Let's scroll down. And here you have explicit constraints. And the weight for this behavior is set to 0. So let's up this to 1. And now the solver will evaluate the constraints. And you can see the stuff is falling down, but it's behaving like wires. It's hanging there. It's stretched very, very long because the force of the gravity is very strong. So instead of minus 9.8, which is correct in a physical sense, let's just use minus 1. So, or even less, say minus 0.5. Because we want a force pulling down, but it's not necessary to have it physically correct. It's still quite bouncy, and that is due to the constraint amount. So this setting here on the grain solver, the constraint iterations, is telling the solver how many constraints are evaluated to pass forces along. So 20 constraints means a force can travel 20 particles. But we have more points than 20, and that means that the pinned particles really propagate only 20 particles along. And the PVD solver is under-enforcing constraints. So if the constraint iterations are not high enough, it will just be bouncy. So let's up this to say 250. If you do that, it's a lot slower, but at the same time, it's now behaving as it should. Because with 250 constraint iterations, the solver has enough constraint iterations to propagate the forces over the whole yarn. And now it's behaving like it should. To make it faster, we can go to the Solver tab and just tick Use OpenCL. Now it will execute on the graphic card, and this will make stuff go faster. Like so. Nice, our wires are simulating now. Now for a custom behavior. We want to add more constraints to the system on a random basis. So some points between the yarns should just start to connect. And this will eventually create the effect of the whole system becoming more and more interconnected. We can add more constraints with a SOP solver with no problem, but it's not necessary to do this. We can just use a geometry wrangle here. So let's create a geometry wrangle. Here it is. And now we have to think about where to execute this. When should the new constraint be added? It's a good idea to add them before the actual solve happens. So here on the pop solver, you have a port for pre-solve and a port for post-solve. That means first everything gets executed that is attached to this port, and then everything gets solved, and then everything gets executed that is attached to this port. And we want to add the constraints before the solve happens. So let's attach this geometry wrangle to this port here. Open the expression editor, and now we will write a little bit of code. We want to add new primitives to points, but not to every point, but on a random basis, and only if some criteria are met. We, for example, don't want to connect points that reside on the same yarn, but we want to connect points that are on different yarns. Then we want to search for the closest point, such that every point connects with the closest point on the next yarn, or of one yarn in the direct proximity of the yarn. So let's implement this. The very first thing is I need a random value. So a float, I call it rval for random value, and this is a rand function. For every point I need different random values, so I need a seed that is per point. I use ptnum here, and then I multiply this with the time to have a different value for every frame, and then just a random number like 1, 2, 4, 5, 6, 8, 7 to make it unique. This is a random value. And now I write an if statement. If this random value is smaller than, say, 0.001, and if the time is smaller than 2, so 2 seconds, then new connections should appear. So brackets. That means I only want to add new connections when this random value is under a certain threshold and only after 2 seconds, because I want 2 seconds of simulation where the stuff is just falling down and settles a little bit before I start adding stuff. Okay, now that I have this in place, let's go on. I want to search for the closest points now, because for every point I want to connect with the closest point. So we need an integer array. I call it near points, square brackets again to indicate it's an array, and then use the near points function and search for the closest point in geometry stream 0 around the current position of the currently processed point. And let's use a search radius of 1 to capture pretty much all the points. And the points will appear in the order of the closest distance. So the closest points will be front in the array, and the farthest points are at the end of the array. Now that we have the closest points, let's run over all the closest points using a for each loop. So for each, count variable is point, and it should run over PNTS over all the points in the near points array. And again, brackets, like so. Now we have all the near points, and we have a loop going over all these near points. And now we want to decide if we want to add a constraint. So first we have to gather some information. And the information we want to gather is the myPrim variable of the closest point. So int, I call this tar myPrim. And using a point expression, I can read the attribute from point ID. So geometry stream is 0. The attribute is called myPrim. And PNT is the ID. Then I need the information if the point is already processed, because I only want one connection per point. So I gather another attribute called processed and store it in a variable called tar processed. Again, a point expression. Same as before, but this time the attribute is called processed, and PNT is the index. And then I need the information if the point that we found belongs to the ends group, because I don't want to add connections to ends. So int tar in group ends is, and this time I use a in-point group expression or function, in-point group, which tells me if a point is in a point group, and geometry is 0. The group is called ends, and PNT is the ID. Now we have quite some information about the point that we found. And now we can write another if statement to decide if we want to use this point to actually create a connection. So if, and curly braces, like so. And now follows quite an if statement here. The very first thing we want to check is that the myPrim attribute of the target point is not the same as the myPrim attribute of the current point, because we only want to connect points that are not on the same yarn. So if tar myPrim not equals myPrim, then we want to add something. And then a logical AND. The next thing is I only want to add a connection if the point has not been processed already. So I check for the processed attribute. And don't wonder where this attribute comes from. We did not create it yet. We will create it later. So only if processed is 0, then please add a connection. And another logical AND. We don't want to add a connection if the currently processed point is in the end group. So we can just check group ends is 0. Okay, now we made sure that the currently processed point, so the start of the new connection, has not the same myPrim attribute as the target point is not processed already and it does not belong to the ends group, so is not an open end. And now we want to check the same for the target point. So tar processed should be 0, 2. And last but not least, tar in group ends should be 0, 2. Let me make this window a little bit bigger. So again, this is quite a bit of writing, but it's quite easy. It's just telling me tar myprim should not be the same as myprim. That means the target point and the currently processed point have not the same primitive. Then the processed variable should be 0, so the currently processed point should not have been processed by the geometry wrangle already, and it should not be in the ends group. And then the same for the target point, it should not be processed either, and it should not be in the targets group either. Now that we checked all this, we can just add the connection. So let's add a connection. We already did this. Int nprim for new prim is add prim. Geometry 0 and polyline. Then add vertex. Nprim is the primitive to add the vertex to. And first we add ptnum, the currently processed point. Then we add a vertex for the target point, 0, nprim, and pnt, which is the target point in our case. Great. Now we added the connection, but we need a rest length for the solver. So we have to add the rest length on the new connection. Let's calculate the rest length. We need the position of the target point. So let's create a variable called tarpos of type vector, and let's just query the position with a point function. 0, the attribute to query is p, and pnt is the ID to query. Now we have the position of the target point, and let's calculate the length of the vector between the currently processed point and the target point. That is just length. And then it is the current position minus the target position. This is the length of the new connection. And now let's set this as a primitive attribute, rest length. Set prim attrib. Geometry is 0. The attribute to set is called rest length. The primitive is nprim. Then length is a value to set, and then we have to tell the function that it should set the values instead of override them or toggle them or stuff like that. And now for the processed attribute. Let's now set an attribute processed to 1 on the current point, because now the point has been processed. And let's do the same on the target point. That has to be done with the same point attrib function. And let's just set the attribute processed on the target point pnt to 1. And we have to specify that we want to set the attribute here too. And last but not least, let's add the new primitive to a group called connectors, because later on we want to shrink these new connection lines. So set prim group 0. The group should be called connectors. And if the group is not present, it will just create the group, and then nprim should be added to this group. 1 is the value, and set again. You see a pattern here. So now let's try if we have some typos here. Oh, yes, we have. A comma is missing here. Let's try again. Still another comma. And another comma here. And another comma here. and yet another comma. Now everything should work. Let's call this node Add Connections. Before we try it out, one last thing, go to the Inputs tab here and set the first input to myself. Otherwise, the geometry wrangle inside of the DOP context does not execute. If you set this, it executes. Now let's test it. Look at this, it's adding connections, but it's adding them immediately after we press play. And we planned on introducing 2 seconds of waiting before it introduces these connections. Let's check why this is. And yeah, we say here if time is smaller than 2, and it should be the other way around if it's bigger than 2. So change this and try again. And now it's falling without adding connections. And after 2 seconds, it's starting to add new connections to the system on the fly. And all without any subsolver. That's very nice, but it doesn't look too good, and that is because these connections have the rest length of the actual length at the moment when they're added, and this rest length does not change. But what we want to do is we want to pull the yarns together. So one last step is needed. We want to shrink the rest length of the new connections in every frame. And to do this, we need another geometry wrangle. Geometry wrangle. This time set this to myself immediately. And we want to add this post-solve. So after the solve and everything, the rest length of the new connection should change. So let's connect this to this merge here, because then first the source will be executed post-solve and then this new geometry wrangle. Call it shrink rest length. And let's make it execute on the connectors group that has all the new connections inside. And the code to write is very simple. It's just add rest length times equals 0.5. Now this wrangle will shrink the rest length in every frame. So let's try this. I obviously did something wrong, and that's because it has to run over primitives and not points, because the rest length is a primitive attribute. So let's try again. And now it's working. Here you have it. Self-connecting yarns using the PBD solver. I know this was quite a little bit of wax, but it's the easiest way, I think, to achieve an effect like this. Although you, of course, can go the subsolver route and do most of the stuff with standard nodes. I hope you learned something, I hope you had fun, and see you next time.